The cloud is a myth. It has no physical location, but the machines running it are heavy, hot, and hungry for land at an unprecedented scale. While headlines focus on software breakthroughs or legal debates about AI personhood, the real bottleneck driving the next decade of robotics and autonomous systems isn't code, it's thermodynamics. As we move from simple chatbots to embodied agents that train in massive clusters, data centers are no longer just server rooms. They are industrial power plants requiring thousands of acres to dissipate heat at gigawatt scales. This video decodes why the future of AI is a land grab driven by hard physics. You cannot cool what you cannot contain. The first thing we must understand is that software can only do so much against the laws of thermodynamics. For years, engineers have promised efficiency through algorithms like early stopping methods in ensemble evaluation. Research shows these techniques can achieve speedups ranging from 2 to 4 times compared to standard ensemble evaluations by deciding when a model has learned enough and should stop calculating. This means you might save time on specific queries or reduce the number of models evaluated per request, theoretically making systems faster and more efficient. But here is where the engineering reality bites. While algorithms can optimize when to stop calculating, the hardware must still process vast amounts of data before that decision is made. That processing generates immense waste heat. You cannot delete the physics of energy conversion. Every joule of computation eventually becomes a joule of thermal dissipation that must be moved away from the silicon or it will melt the machine. This creates a fundamental constraint on power density that air cooling simply cannot solve at scale. To visualize this, imagine an engine block running at maximum output without a radiator large enough to cool it down. In traditional data centers, fans and airflow act as that rudimentary radiator, but they hit a hard ceiling when you push densities toward the gigawatt scales required for modern autonomous systems. The heat flux becomes so intense that standard air cooling fails completely. To manage this, we're forced into liquid immersion cooling and massive geographic footprints where water sources exist to absorb that thermal load. You cannot just stack servers higher. Eventually, the building itself becomes a furnace unless you have space dedicated to moving that heat away from the compute cores entirely. This is why the infrastructure for intelligent machines looks less like an office building and more like a heavy industrial facility with massive cooling towers and substations. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The cost of thinking at scale forces us to rethink where these systems can live. The theoretical limit for optimal ordering in ensemble evaluation suggests a 4 approximation bound, meaning that even with perfect software optimization, data centers must be built with redundant power and cooling capacity that scales linearly with model complexity. This requirement drives the need for localized land acquisition near renewable energy sources rather than urban centers where real estate is scarce. But cheap electricity isn't available. We are seeing a shift from co-location in cities to massive campus-style developments on rural land because you simply cannot fit gigawatt-scale loads into existing city grids without tearing up infrastructure that serves millions of other users. The physics demands space for transformers, water sources for heat exchange, and grid stability that urban environments can no longer provide. This reality fundamentally changes the narrative from AI as a disembodied cloud to a physical land grab driven by engineering necessity. Unlike speculative discussions on AI legal personhood or generative art projects using quadruped robots as performance props, the reality of autonomous systems requires compute that runs continuously in harsh environments. The infrastructure supporting these machines, where they train and where their digital twins live, is a physical plant limited by the laws of thermodynamics. You cannot cloud away the heat generated by training models for embodied agents. You must physically move it to land with access to water and power grids capable of gigawatt-scale loads. This is not about tax breaks or zoning loopholes. It is about the hard requirement that every watt of compute needs a corresponding path to dissipate its waste heat into the environment. The implications for robotics are profound, because autonomous systems do not exist in isolation. Humanoids, self-driving vehicles, and industrial automation all rely on models trained in these massive clusters before being deployed to the physical world. The land grab is the foundation for the next wave of intelligent machines. If we cannot solve the heat dissipation problem at scale, the training times for new capabilities will stretch into years, or worse, become impossible due to thermal throttling that prevents high-density computation from running continuously. We are entering an era where the availability of land with sufficient power and cooling capacity becomes as critical a resource as the code itself. The competition is not just between software companies, it is between physical infrastructure requirements and the finite resources available on our planet. As we look toward the future, the distinction between smart systems and their supporting hardware will become even sharper. We cannot separate the intelligence of an autonomous vehicle from the power plant that trained its brain or maintained its simulation environment. The next decade will be defined by how quickly engineers can build out this physical backbone to support the explosion in computational demand. While we debate legal frameworks for AI rights, the real story is happening on thousands of acres where transformers hum and water flows through cooling loops to keep silicon from melting under the weight of global intelligence. The future of robotics depends not just on better algorithms or more sophisticated sensors, but on our ability to manage the physical cost of computation at a continental scale. The bottleneck is no longer code, it is thermodynamics. We're building an industrial machine for the age of artificial intelligence, and its size is dictated by the laws of physics that govern heat and power density in every single chip we use. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.